For my nanotechnology research midterm, I decided to look into how nanotechnology is impacting the energy conservation field, particularly the solar industry. When looking into the solar industry, it's important to remember that the Earth intercepts approximately 173,000 terawatts of power every day, which is 10,000 times more power than our planet's population uses. So there is potential in this field to create revolutionary new sources of power. The first main thing to look at is how do solar panels convert solar energy into electrical energy. Solar panels are made up of smaller units called solar cells. Solar cells are made up of a variety of materials, but to simplify the explanation, we're going to look at a silicone-based cell. To start with, silicone atoms are connected to each other with 4 bonds, keeping the electrons in place so that no current flows through the circuit. These silicone atoms are sandwiched between 2 conductive layers. So when the solar cell is struck by photons, it knocks out the electrons. Once these electrons are knocked out, they're free to move around. And once they're free to move around, since we have our 2 conductive layers, all of the electrons go to the N side. And once they get to the N side, they're going to go through an electrical circuit, some kind of circuit, and come back to the P side where they're going to fill in the voids or the holes. So this is how solar cells transform solar energy into electrical energy. So now that we have the basis of how solar cells work, let's go into describing the 3 generation types of solar cells. The first generation of solar cells are mainly silicone-based. Some pros to them is that they're highly stable, and silicone is an abundant element, so there's plenty of it to go around. The cons with it is it's not scalable. These cells are, fairly large, and it's not efficient to use them. They're expensive to manufacture. They reach high temps. They use a lot of material, and they have to be done in a vacuum process to create these cells. The second generation gets a little better. They're called thin film solar cells commonly. Pros to these are that they're only a few micrometers thick, so they're flexible and they're more efficient, and it's cheaper to manufacture. It's still not at an ideal temperature, but it's lower temperatures and lower material consumption. It still needs to be done in a vacuum process. The cons to these is that it's not very stable, and they're made of toxic materials and scarcer elements than silicone. The third generation is still up in the air. There's a lot of research going on it. They're made in a lot of small molecules and polymers. Some pros is that they're reaching a lot better efficiencies with them, which we'll explain a little bit, and they're getting cheaper to manufacture. And the cons is that still we're not sure how it's going to operate. So I found this data, which was done in an MIT lab, and I thought it was great to see how we're improving efficiency-wise between the 3 different generations. And I also liked that it showed the cost per watt and how we're slowly getting better and getting more practical, considering the fossil fuel cost from FP&L was found to be 1 cent per watt. So I thought this graph was a great way to show how we're evolving in different solar cells. Now that we've looked at the 3 different generations of solar cells, I figured we'd look at some issues with solar power right now. The first one's kind of boring. It's inconsistency in solar distribution, which everyone knows. The sun, the Earth rotates. We have days and nights. The second one gets a little more interesting, in which photons are actually reflected off of solar cells, because solar cells only take in light at wavelengths between 380 and 750 nanometers. So that's only between the violet and red range of wavelengths. The third problem that we're getting is, once we talked about earlier, those electrons getting hit by photons and getting knocked out of place, is the electrons coming back into the holes before completing the circuit. So it's lost energy. Now that we've looked into some issues with solar cells, let's look into some solutions that nanotechnology is providing. So one of the first ones I wanted to look into was the issue with light not being able to be absorbed by solar cells because it was out of the bandwidth of wavelengths. So one solution to that was this nanophotonic crystal and nanotubes that were basically being used together to absorb dissipated heat from the solar cell, which was deemed unusable and pretty much you can't use it. And when they're integrated together, once this crystal is heated, it re-emits a narrow light within the solar cell, which is between the ranges of violet and red, which is what the solar cell needs to absorb. Another example of how nanotechnology has been affecting the solar industry is a study that was done with dye-sensitive solar cells. Photoelectric nanochannels were added to enhance the photoelectric conversion efficiency. The results showed dramatic improvements in volatile cell performance. This concludes my presentation on how nanotechnology is affecting the solar industry.